Hello everyone, I'm Chuandong from Peking University. I'm delighted to be here to present our work, HUGESCOPE. This work clearly solves the hot bloat problem under virtualization. First, I want to introduce some background about virtualization and the huge page. During address translation, the virtual address of guest application need to be translated into guest physical address through the guest process page table, and then it is need to be translated to host physical address through the nested page table. So with base page configurations, address translation requires 24 memory accesses due to the two-level page table traversal. So huge page is widely used to speed up the process. It can reduce the memory access to 15. Also, huge page can increase the TLB coverage and reduce TLB misses. Therefore, huge page can bring us considerable performance improvements across a wide range of benchmarks. However, using huge page is not a panacea. The system usually leads to trade-off between performance and page management granularity. When enabling huge page, the 2 megabytes physical memory shares the same permission bits in the level 3 page table entries. And the hypervisor knowing nothing about base pages. Of course, when you're using base pages, the hypervisor can perceive and manage this memory at more finely. For example, each base page has its own access and dirty bits, but the price is the worst performance. Things get worse when the access to a huge page skewed towards a few base pages. The hypervisor will mistakenly classify the whole huge page hot due to the shared access and dirty bits. Additionally, if there are many such skewed accessed huge pages, the hypervisor might think the whole memory of the VM is hot, but in fact, there is only a few base pages are frequently accessed. We call this phenomenon hot bloat. Hot bloat is widespread. Many benchmarks show such access skewness. A typical application is database. The complementary CDF graph shows the memory access behavior of Redis reported by the hypervisor with huge page and base page configurations. This graph shows that about 90% of the memory is accessed more than 70% of the time with the huge page configuration. But the results of base page configuration are completely opposite. Hot bloat affects technologies such as tiered memory management, which aims to scale VM memory using slow memory such as persistent memory, while maintaining the performance. Tiered memory management use page tracking, page classification, and page migration to put hot pages into the fast memory and put the cold pages into the slow memory. But hot bloat can mislead the hypervisor into treating all memory of the VM hot, mistakenly put cold base pages into the fast memory. A macro benchmark shows that the more the such skewed huge pages, the worse the performance of the system. Another example is page sharing, which shares pages with the same data using copy on write. Because the probability of a huge page with the same contents is extremely low, the system needs to consider whether a huge page needs to be split. Policies include keep huge, split all, and split cold huge pages. Keep huge policy minimizes the memory sharing. Split all policy reduces performance. So the split cold policy seems to offer a balanced trade-off. However, hot bloat makes hypervisor hardly find the cold huge pages, thus degenerating the split cold policy into the keep huge policy, which means it also gets a low memory savings. The previous work cannot solve the hot bloat problem under virtualization well. Another common method is page fault-based tracking, which mark all the pages as protected, and it can get accurate address through page fault when access happens. However, under virtualization, VM exit for each access severely degrades performance. Another idea is to monitor the sampling pages to reduce the overhead. But the experiment shows that there is always a lag in sampling, and it can't respond effectively to the memory access changes. Finally, it is considered to use Intel PBS, which is based on the hardware counter, but at present, the hypervisor can't use PBS to track memory access information inside the guest VM, mainly because the PBS buffer have no virtualization support. An intuitive solution to the hot bloat is to split all the huge pages and monitor the internal base pages, and then coalesce the huge pages back. However, the overhead is unacceptable. Every split and coalesce will cause a corresponding VM exit, and those two operations themselves have high overhead, as shown in the figure that we profile the corresponding interface in the Linux KVM. But this figure presents an opportunity to us. While the page metadata updating is slow, the page table updating is fast. And the page metadata updating is not necessary for page tracking. What we want is just each base page has their own access and dirty bits. So our basic idea is just to split or coalesce the page table, not the page. But this will cause another problem, that is how to ensure the consistency of page table and the page metadata. Fortunately, the two-level address space abstraction in virtualization bring us some insights. First, the modification to the first level, that is the guest process table, and the second level page table, that is the listed page table, are highly asymmetric, which means although the guest page table is frequently accessed, the listed page table of the VM rarely accessed and modified once the listed table is established. The second insight is that modifications to the listed page table by the hypervisor is limited to a few and stable interfaces. For example, there are only 11 places in Linux KVM, and those interfaces remain stable for many years. Therefore, our solution is to split and coalesce the second level, that is listed page table, and bypass all the other operations, and we maintain the consistency based on those two insights. So based on those observations, we propose HUGESCOPE, a lightweight, effective, generic, and modular solution for hot bloat under virtualization. It features a two-phase page tracking, a comprehensive page size policy, and a modular interface. We then integrate HUGESCOPE into the tiered memory management and the page sharing system. We use the two-phase page tracking, including a coarse phase and a fine phase, to track the memory access behavior of virtual machines. Page tracking in the coarse phase is similar to the traditional page table scanning method, which periodically check and flash the access and the dirty bits of all the listed page table entries. After coarse phase, we can get some hot huge pages. For those hot huge pages, we then use fine phase tracking to find whether there are some skewed accessed huge pages. Page tracking in the fine phase splits the listed page table and then tracks the memory access at the base page granularity, and finally coalesces the listed page table back. Fine phase tracking bypasses all the metadata related operations, and it only updates the listed page table and flashes the related TLB. Metadata updating bypassing creates an inconsistency between the metadata and the listed page table. The page metadata tells us this page is a huge page, but the listed page table tells us this page is a base page. But the inconsistencies are rarely perceived by the hypervisor due to the our insight 1, which is the listed page table, is rarely accessed by the hypervisor. But once the hypervisor finds inconsistency, it will cause a conflict and undefined behavior. So according to our insight 2, which is hypervisor always access listed page tables through a few and stable interfaces. We just need to add some code hooks before those interfaces. We coalesce the listed page table back before the modification and access happens. Then we need to decide which pages need to be split or coalesced. First, we define page skew ratio to qualify the access skewness of a huge page. Then we define hot pressure to represent the tolerance of the system to the hot huge pages. After coarse phase tracking, HUGESCOPE can get the initial hot pressure by the monitored hot huge pages numbers and the expected huge page size. After fine phase tracking, HUGESCOPE can get the distribution of each huge page's page skew ratio. When the hot pressure is high, HUGESCOPE splits the pages from large to slow according to the page skew ratio. If there is no hot pressure, HUGESCOPE will coalesce the page from small to large according to the PSR. We abstract the interface according to the ability of the HUGESCOPE and provide a flexible and modular interface implementation. Generally speaking, they are divided into 3 categories: coarse phase tracking switch, fine phase tracking switch, and policy setting interfaces. The figure on the left is the pseudocode that we rely on HUGESCOPE interface to realize tiered memory management. We use HUGESCOPE to optimize tiered memory management and page sharing. For tiered memory management, HUGESCOPE replaces the original page monitoring mechanism, and after page classification, we track and split huge pages with the hot bloat problem, and then the tiered memory management can accurately put hot pages into the fast memory. For the page sharing, we use 2-phase tracking and apply original content scanning and customize split based on scanning results to ensure only huge pages with identical content base pages and hot bloat split. Here is our experimental configuration. In the tiered memory scenario, local DRAM served as fast memory, and we use Intel Optane memory as slow memory. We focus on 3 main results here: page tracking efficiency and the HUGESCOPE's optimization for the 2 subsystems, tiered memory and the page sharing system. First, for the page tracking overhead, we can find that tracking by split pages and high frequency PEBS cause significant performance slowdown. However, for our HUGESCOPE, the overhead remains low even in multi-VM and different huge page numbers. For the tracking accuracy, we can find that HUGESCOPE can track with split pages are accurate as base page configuration, while monitoring under huge page configuration shows serious hot bloat. Sampling-based methods like sampling page splitting and PEBS are highly inaccurate. So the 2-phase tracking of HUGESCOPE cause low overhead and accurate as base page configurations. In tiered memory management, we compare the performance of HUGESCOPE and VTMM with huge and base page configurations. In Redis and MongoDB, the results of huge page configuration are even worse than that of base page configurations. HUGESCOPE outperforms both by combining the efficiency of huge pages and avoiding poor decision triggered by the hot bloat. You can find other results about other benchmarks in our paper. In the page sharing scenario, we found that previous policies have a trade-off between memory saving and performance, either perceiving performance with poor sharings or having low performance with extensive sharing. HUGESCOPE effectively balances both, maintaining considerable performance and memory sharings. In summary, we solve hot bloat based on the insight that the second level page table under virtualization is stable and accessed by a few and stable interfaces. The two-level abstractions asymmetric access characteristic inspires us. Thank you.